Hello everyone. What we have done so far is we discussed what is indeterminate structures, and there are majorly two different kinds of methods for solving them. One is force method and one is displacement method. We introduced what is force method, just the introduction. What we will be doing today is we will introduce what is displacement method. Okay, we won't go in details of the displacement method, as we did not go in detail about force method. Just the concept we will introduce today, and the next week onwards, when we will apply those methods to different problems, those concepts will be probably more clear. Okay, so today's topic is analysis of statically indeterminate structures. Same, we have been continuing an introduction to displacement method. Okay, if you remember, in the last class we stopped at this slide. Okay, this when we introduced what is force method, and finally we arrived at the force displacement relation as this. Okay, in this case, forces are, one is moment applied at A and one is concentrated load applied at P, and the displacements are theta A, rotation at A, and delta B is the displacement at point P, and this is the relation. Okay, and we also we also saw that this is flexibility matrix, right? And all these coefficients alpha and F, we can see these are all flexibility coefficients. We also saw that this matrix is a symmetric matrix. So, alpha A B, this term and this term, they are same. Okay. So, alpha A B is equal to alpha B A. Now, I ask you, please check why it is not accident. If you even for different structural problem, if you see and if you compute the flexibility matrix, you will see those matrices are symmetric matrix. And what exactly it says, you know this theory. This is essentially so these are the matrix, you can see that this alpha A B is equal to F B A, this is a symmetric matrix. Okay. Now, what exactly this is says, this is the reciprocal theory of reciprocal deflection, Maxwell-Betti law of reciprocal deflection. What it says is, we already discussed this reciprocal theorem when we were discussing virtual work principle. What it says that if you put m is equal to 1 and p is equal to 1, what is alpha A B? Alpha A B is essentially the rotation at theta A due to p. And what is F B A? F B A gives you the rotation displacement at B due to applied load m. So, if you take both are unit, m is equal to 1 and p is equal to 1, then alpha A B will be the rotation at A due to unit load applied at B, and then alpha B A will be the deflection at B due to the unit moment applied at A, and as per the reciprocal deflection law of reciprocal deflection, they should be same. So, this is that is why this is same. Okay. So, we already have seen it in the form of law, but now it is a demonstration of that law, that if you take any structural problem, it is a consequence that the matrix that you get that is symmetric. Okay. Now, so this is the matrix what we have, just the same matrix, but only L by 48 EI term taken out. Now, if we invert this matrix, if we invert this relation, means now this relation give you theta, force displacement is equal to this flexibility matrix into force, right? If we invert this relation, what we get is, this is called flexibility matrix, right? We discussed it. Now, if we invert it, then what we get is that inverse of this matrix is this. So, now we will get the force is equal to something into deflection, and this something is called, it is the stiffness matrix. If you remember how the displacement is related to force, we discussed that if F is the flexibility, if F is the flexibility, then flexibility into force is equal to give displacement, right? Give displacement. And if K is stiffness, then what we get is stiffness into delta displacement is equal to give you the force. We have demonstrated this through through a spring problem, okay, in the last class. So, this matrix is called stiffness matrix. So, this is inverse of the flexibility matrix. Now, one important point here you can note that see Young EI is the EI is called flexural rigidity of a beam, because if Young's modulus is more, means if the Young's modulus is more, then the beam undergoes less deformation. Similarly, if the second moment of area is more, then the beam undergoes less deformation. So, together their effect are similar. So, together EI is called flexural rigidity. Okay. So, if EI is more for a given problem, for a given beam or a given structure, if EI is more, means the flexural rigidity of the member is more. So, the deflection of the member will be less. So, the structure becomes more stiffer. So, that is why this is called stiffness. Now, on this case, if EI is less, then what happen? The member undergoes more deformation. The member becomes, or the structure become more flexible. It undergoes more deformation. So, this is flexibility matrix. Now, why I am showing this slide? Because you see, in force based method, in the force method, these flexibility coefficients plays a very important role. They are essentially the building blocks of force method, and if you do it in a matrix form, force matrix method, then the flexibility matrix is the building blocks. Now, similarly, in displacement method, it is the stiffness matrix is the building blocks for displacement based method. Okay. So, what we are going to introduce today? So, essentially it is the same load deflection relation you are writing, but in the force method, that relation is written in flexibility format, and the in displacement method, that relation will be written in stiffness format. Okay. Now, before we introduce the displacement method, there are few things which is important to the few concepts which we will be using, which is very important in displacement method. Before that, there are three major displacement based methods we will be studying here in this course. One is slope deflection method, moment distribution method, and direct stiffness method. Details of this method we will see as we derive those methods and apply to different problems. Now, see, as I said, you see, we know what is static indeterminacy, right? We know what is when a structure becomes statically indeterminate or statically determinate structure. And when we introduce static indeterminacy, I also mentioned there is another term called kinematic indeterminacy, and we just mentioned the name, but we did not discuss anything about kinematic indeterminacy. And I told you, whenever it is required, whenever we come across this kinematic indeterminacy, we will discuss that. Now, this is the time when we need kinematic indeterminacy. Okay. Now, before we introduce what is kinematic or define kinematic indeterminacy, just recall what was degrees of freedom. Probably in the first week we introduced what is degrees of freedom. It is the degrees of freedom of a mechanical system is the number of independent coordinates required to completely specify the configuration of the system. In two-dimensional, there are 3 degrees of freedom at a point, which is 2 translation in x and translation in y direction, and rotation on xy plane. So, since we are all the concept that we are studying here, that will be that we have been applying that to plane structure. So, for us at a given point, total degrees of freedom a point can have is 3. 2 translation and 1 rotation. But when we extend this concept to space structure, say space frame or space truss, then at any given point the total degrees of freedom will be 6, 3 translation and 3 rotations. Okay. Now, this is degrees of freedom, we know this. Okay. Now, what is now when a skeletal structure deforms, then what happens when a skeletal structure is loaded? Then the joints undergo displacements either in the form of translation or in the form of rotation, because that is the degrees of freedom a joint can have. Just to make it more clear, suppose there is a truss here. It is a statically determinate truss. Let us see, because it has four joints. So, number of equations are available 8, and then how many members it has? 1, 2, 3, 4, 5 members, and then 3 reactions to 5 plus 3, total 8 unknowns and 8 equations available. It is a statically determinate structure. Now, when it is applied some load, say if it is applied to a load something like this, a load here, and at point you apply a load here, then it undergoes deformation like this. So, point B comes to B dash, point C goes to C dash, and point D goes to D dash. Okay. Now, so what happens? These now take another example of a beam. It is a beam AC, which is subjected to maybe any random load on this. And it is transversely deformed like this. So, in this case what happens? The joint A undergoes rotation and joint C undergoes rotation. Okay. Similarly, if you take a frame like this and it is subjected to again a horizontal load something like this, then the blue line that we can see, that is the deflected shape. So, point B goes to B dash, point C goes to C dash. And point A and D, they are fixed supports, so they neither translate nor rotate. So, what happens when a skeletal structure is subjected to any kinds of load? Their joints, in this case joints are A, B, C, D, these are the joints. Those joints, they undergo deformation. They undergo deformation either in the form of translation or rotation or both. For instance, in this case it is only translation, but many other cases it could be only. In this case it is joint A and C. Joint A is only rotation, joint C it is a roller support, so it can rotate and it can translate in this direction as well. So, it is rotation plus translation. And for this case joint B goes here, joint C goes to C dash. So, this is also combination of translation and rotation depending on the type of joints we have. Okay. Now, then what is kinematic indeterminacy? Kinematic indeterminacy is, in a skeletal structure, the kinematic indeterminacy is the total number of degrees of freedom at various joints. Okay. Just to understand in a better way, consider the same truss here, which undergoes deformation like this. Okay. Now, you see the point joint A cannot translate. In this case, since it is a truss, there is no rotation allowed in any joint. So, it is only translation. So, mode of deformation is of any joint is only translation. Now, joint A does not undergo any translation because it is hinge joint, but joint C, which is roller support, it cannot move in y direction, but it can translate in this direction, but it cannot translate in y direction, and joint A in both the direction, these translations are restricted. But all other joints, joint B, joint D, they can translate in both the directions, isn't it? Now, at every joint, how many degrees of freedom we have in this structure? At every joint we have 2 degrees of freedom. Okay. What are those 2 degrees of freedom? Translation in the x direction and translation in y direction. There is no rotational degrees of freedom because all the joints are hinge joint rotation. There is okay. Now, so what happens? Then you see how many displacement unknown we have here. You see joint B we have horizontal displacement and also we have vertical translation. Joint C we have horizontal translation and joint D we have horizontal translation as well as vertical translation. Then joint A there is no translation and joint C there is no translation in horizontal direction, in vertical direction. So, how many degrees of freedom at the joints, total degrees of freedom at the joints we have is 1, then 2, then 3 then 4 and then 5. So, in this structure, if you see only the joints, then the total degrees of freedom at various joints are total 5. At this point B, we have 2 degrees of freedom. At point D, we have 2 degrees of freedom. At point C, we have just 1 degrees of freedom. At point A, there is no degrees of freedom, because joint A cannot go anywhere. Okay, it is supported. So, in this case, in this problem, the kinematic indeterminacy is 5. Okay. So, the kinematic indeterminacy is the total number of degrees of freedom at various joints. So, we know what are the degrees of total degrees of freedom we have at various joints, and that would be the kinematic indeterminacy. Okay. Now, take one example. Suppose this is the structure, the same structure, same truss, but all joints are we have simply support at all the joints. So, what happens then? What is the kinematic indeterminacy of the structure? The kinematic indeterminacy of the structure is 0, because joint A cannot translate anywhere, because it is supported. Similarly, for joint B, C, D, all the joints are supported, so it cannot go anywhere. So, the degrees of freedom at all the joints are 0. So, total degrees of freedom is 0. So, kinematic indeterminacy of the structure is 0. So, when the kinematic indeterminacy of the structure is 0, this structure is called kinematically determinate structure. Now, see the difference between static indeterminacy and kinematic indeterminacy. You see, for this truss, it is not statically determinate truss, because if you have to find out reactions, how many reactions we have? 1, 2, 3, 4, total 8 reactions we have, and then 1, 2, 3, 4, 5, total 5 member forces we have. So, total 13 unknowns, but how many equations are available? Only 3 equations. So, this structure is statically indeterminate structure, but it is kinematically determinate structure. Okay. So, kinematic indeterminacy of the structure is 0. Okay. Now, see just one more example. One more example for truss itself. So, you see, take a truss here. We draw quickly a truss. Okay, and these all are hinges. Okay, all are hinges. Now, we have support here. Say we have a support here, and we have a roller support here. So, what is the kinematic indeterminacy of this structure? You see, at this point there is no, because this point neither translate in this direction nor translate in this direction. You see, this point can translate in this direction as well as in this direction. This point also can translate in this direction as well as in this direction. This point can translate in this direction and this direction. This point can translate only in this direction. There is no vertical translation, and this point also can translate in this direction and also in this direction. Then what is the kinematic indeterminacy it has? It is 1, then 2, 3, 4, 5, 6, 7, 8 and 9. So, the kinematic indeterminacy is 9. Kinematic indeterminacy or NK is kinematic indeterminacy is 9. Okay. Now, what is static indeterminacy? Static indeterminacy NS is check how many joints we have. 1, 2, 3, 4, 5, 6 joints. So, J is equal to 6. How many members we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So, member is 9 and the reactions R is equal to 3. So, we know that 2J. So, total equations available is 2 into 6, 12 equations available. How many unknowns are? 9 plus 3, 12 unknown. So, static indeterminacy is 0. So, this is static indeterminacy is 0. So, it is statically determinate structure. Okay. Now, for kinematic static indeterminacy, we know the formula is m plus r minus 2j. If you remember, this was the formula, m plus r minus 2j. Now, for kinematic indeterminacy also we can similarly we can write per each joint the degrees of freedom are 2. So, total number of joints here it is 6. So, total number of joint is j is equal to 6. So, total degrees of freedom is 6 into 2 is equal to 12, means 2 j is equal to 12, and how many restraint we have? Here 2 restraint and here 1 restraint. So, r is equal to 3. So, it is 2 j minus r is equal to 9. So, this is the kinematic indeterminacy of this structure. Okay. Now, similarly for any structure you can find out the similar way for any truss you can find out the kinematic indeterminacy. Okay. Now, so let us take this was for trusses. Now, let us take for beam. Suppose this is again a simply supported beam. Now, two joints A and B, and if it is subjected to some kind of load, random load like this, okay, and it deforms like this. The blue is the deform shape. Okay. Now, if it deforms like this, then what happens? Joint A, it undergoes deformation. Joint A is a hinge support, so it can only rotate, and joint B is the roller support. So, what are the only constraint at joint B is the vertical displacement, but the releases are it can allow rotation and it can also allow translation in horizontal direction. So, now if you see, these are the these are the degrees of freedom at various joints. Joint A, only it rotates. Joint B, it rotates, and also due to the horizontal since it is a roller support at B. So, roller support can also move in this direction. Okay. So, in this structure, if we only concentrate at the joints, then at joint A we have just 1 degrees of freedom, which is theta A, rotation at theta A, and joint B we have rotation, which is theta B, and also at joint C translation. So, if point B goes to B dash, because it is roller support and motion in this direction, translation in this direction is allowed. There is no constraint against horizontal movement. So, in this case, total degrees of, then what is the kinematic indeterminacy? Kinematic indeterminacy is 3. 1 degrees of freedom at A and 2 degrees of freedom at 2, total kinematic indeterminacy is 3. Now, there is one important point here. You see, all these you see, what does it mean when we say that joint A can rotate and joint B can rotate? What is the effect on the deformation of the structure? Okay, because joint A can allow rotation, joint B can allow rotation, the deformed shape will be like this. Okay, now, but still even after deformed shape, even in the deformed shape, if we don't consider right now this part, if we only allow say joint A can rotate, it can rotate about A, but the point A, the joint A still remains at the same position, right. Similarly, if we only see the rotation at joint B, the point B still remains at the same position, but it rotates only about that point B. Okay. But what does it mean that when we allow the translation at joint B as well? So, when the translation is allowed at joint B, means if the joint B is initially at this point, then after deformation the joint B takes the position B dash. Okay. It means that initially the length of the beam is AB, it was AB, now the length of the beam becomes AB dash. Okay. So, the length of the beam is now different, means this translation will cause change in length of the beam, means it causes axial deformation in the beam. Okay. Now, if we neglect the axial deformation, if we assume that axial rigidity of the member is very high, okay, if we neglect that deformation, then in this case, if we allow axial deformation, the degrees of freedom are the rotation at A, rotation at B and delta H at B. Now, if we allow axial deformation, then if we do not allow axial deformation, means if we assume that it is axially rigid, axial rigidity is very high, then this mode of deformation, there will be no this mode of deformation. Okay. So, this is neglected, and if you neglect that, then the kinematic indeterminacy of this structure is 2. Okay. Kinematic indeterminacy of this is 2. Okay. Now, okay. Now, we will see some example for kinematic indeterminacy here quickly. Some of the problem, for instance, you see, we'll stop here now, and we'll see some more example on kinematic indeterminacy, and then once we know the kinematic indeterminacy, then we'll introduce what is displacement method by comparing their steps with force method. Okay, thank you.